Hello and welcome to Ch15 3004 Lecture 10, External Flow, Drag and Lift. This is going to be sections 15.1 to 15.4, and then we're going to continue with Lecture 11, 15.5 to 7. This is about flow around something, so maybe we've got an object moving through a fluid, like a propeller or an aircraft, or from a relative perspective, flow moving over an object from the object's perspective. Whether that's an aircraft or a plant, the flow is moving around the object in external flow rather than through the object like it was in internal flow. Okay, some terms. Free stream velocity is the velocity of the fluid approaching the body. This is what the speed of the fluid is far away from the influence of the body. Right around the body, the velocity is going to be changing from around different parts of it as it flows past the object. So imagine the car is moving at 60 miles an hour in stationary air. The free stream velocity would be 60 miles an hour, and that would be the speed up here. But right at the car, the speed is going to be different. So relative to the car, at the car's surface, the velocity is 0 from the no-slip condition, and it's going to have some complicated velocity profile around it. Free stream velocity is the one far from the body, relative to the body. Two-dimensional flow means the body is very long in a direction perpendicular to the flow. So the cross-section of an aircraft wing, we can say the wing length is kind of long, and we'll approximate that as two-dimensional. That's a reasonable approximation, but we'll see where that breaks down. Axis-symmetric flow means that it has rotational symmetry about an axis parallel to the flow, maybe like a rocket moving through the air. 3D flow means that you can't make these approximations of two-dimensional or axis-symmetric flow. Another thing that we can talk about rather than symmetry is compressibility. Incompressible flow means the density of the fluid doesn't change appreciably due to the flow itself. This would be true over cars, submarines, buildings, in contrast to compressible flow, where the density of the fluid changes throughout the flow. This happens in gases at high Mach numbers, no longer negligible around Mach number greater than about 0.3. You actually get shock waves at Mach numbers of 1. So supersonic jets, rockets, missiles, that sort of thing. Streamlined bodies are built to contour to the streamlines the flow would want to have, and therefore have a lot less drag than bluff or blunt bodies. You can see the effect of this in the required power to move at 60 miles an hour in a modern, more streamlined car versus an older, less streamlined car. 15.2, drag and lift. Drag force is the force of the fluid on some body that's in the fluid in the direction of the free stream flow. So if we have flow moving from left to right here in the direction of this arrow, the drag force would be whatever force this fluid creates in the same direction, in contrast to the force perpendicular to that, which we call the lift force. The actual total force is the resultant of adding those two together, so the vector sum of the lift force and the drag force. Drag and lift coefficients are functions of shape and Reynolds number, and determine the drag and lift force as functions of the frontal, or sometimes plane form, area and the kinetic pressure. So we have kinetic pressure, half rho v squared, and we have the area term here. Then the force of drag would be the drag coefficient multiplied by those things. And the force of lift would be the lift coefficient multiplied by those things. This depends on shape. So the shape would change if you change the physical shape of the airfoil, or if you change the relative shape by changing around the angle of attack, so the shape seen by the fluid. And the other thing that it depends on is the Reynolds number. So these constants depend only on shape and Reynolds number, and not on individual fluid parameters like the density, the velocity, the actual area of the airfoil or whatever shape you're talking about. Reynolds number, as before, is defined as rho over mu times v times some length scale, except rather than hydraulic diameter, the length scale has to be defined by the picture. So we'll see in a future section here that we're always going to be labeling what length we're talking about when we make these definitions. Okay, so that's the Reynolds number for external flow and the definition of drag and lift coefficients in terms of the drag and lift force, where those are defined as the forces parallel and perpendicular to the flow, respectively. Drag and lift force are combinations of all of the forces of the fluid due to the motion of the object in the fluid. So these include the shear force from viscous effects, so this boundary layer and causing a change in the fluid velocity from the no slip condition at the surface to the free stream velocity as you move farther away, and the effect of having a different pressure on one side of the object than the other side. When we were dealing with flow inside pipes, we were only ever dealing with friction caused drag, except for possibly those minor loss coefficient parts, and weren't dealing with this other kind called pressure or form drag. For external flow, this is a huge effect, often a dominant effect at higher kind of human scale Reynolds numbers. The other thing that we can be concerned with drag force is the terminal velocity. If you have something that is falling, then as it increases in speed, then the drag force is going to increase until eventually you have a balance between the drag force and the buoyant force and the weight. So buoyant force, not considered part of the drag because it exists independent of the fluid motion. So the actual terminal velocity, if we want to be exactly precise, would be where the drag force is equal to the weight minus the buoyant force. 15.3, friction and pressure drag. As we mentioned in the last section, friction drag, aka skin friction drag, is due to the shear force and acts tangent to a surface, while pressure drag, also known as form drag, is due to the pressure and acts normal to the surface. Generally, friction drag dominates at low Reynolds numbers, while form drag dominates at high ones, but this is not true for all the shapes. Flat plates aligned with the flow, like this one, have no frontal area, so the drag is entirely friction drag at all Reynolds numbers. Streamlining bodies greatly reduces the pressure drag, but not the friction drag. So depending on what Reynolds number you're at, streamlining may not make much of a difference. So at the particular Reynolds number shown here, we can say that the drag from the friction drag on the flat plate here is a lot lower than the form drag on this orientation of the flat plate. And the cylinder here, cylinder coming out of the page, has a drag that's in between both of these, but is going to have a drag coefficient closer to that of the flat plate, which is entirely form drag. So if you want to see a cool video of this, look up a video on vortex shedding, and you'll see what this looks like in time. Vortex shedding around a cylinder. Okay. Here we have a streamlined body, and we're going to be looking at how the ratio of d, the diameter across this, or the width of this thing, to the length of it compares. So how long do you want to make it compared to the width? If you make it too long, so you have a really low d over L, then the pressure drag isn't reducing anymore, and you're just increasing the friction drag by making it longer. On the other hand, if you don't make it long enough, then you get this flat plate effect, which is increasing the drag too. So the optimal streamlined shape in terms of a drag coefficient defined as FD over half rho V squared times LD, the kind of approximate scaling with cross-sectional area, turns out to be somewhere of a balance between these two. So that's why you have these similar looking streamlined teardrop style shapes for all kinds of different bodies. This ends up depending on what Reynolds number and what kind of environment you're going to be moving this shape around in. So here's another one. How, if you take a cylinder, how should you scale it in elliptical terms if you make it longer relative to its thickness? And it turns out that if you make it a fair bit longer than the drag coefficient on this thing, defined as this, ends up scaling down a fair bit. So this is the limit of a flat plate. So this is when L goes to 0. And then as L scales off towards infinity, you have the drag coefficient going down and down. To understand why form drag or pressure drag is such a big deal suddenly for external flow, we have to consider what's going on with separation. So if flow is smoothly going over something and then leaves it like it does as it flows over a waterfall here due to momentum, we have what's called a separation point. Even if there isn't a change in the actual fluid where it's going to air suddenly, then you still have this, say underwater, if there's a ridge here, we'd have a separation point and a separated flow region, which doesn't connect, none of the streamlines in here reach the streamlines in free flow. So this is around an object what creates a wake region, and the wake region ends up with a fair bit lower pressure than in front of the object, the side that's facing the fluid. Here the flow is going from left to right around this tennis ball, and the wake region difference in pressure from the front of it causes a massive amount of form drag. Now look at what happens when we take this airfoil and we start increasing the angle of attack. We go from a reasonable lift and a large drag force to higher lift, higher drag, and then eventually the drag gets higher than the lift, and we might end up with some kind of a stall condition. We'll look in more detail at airfoils later. 15.4, drag coefficients of common geometry. So here we're going to take some shapes and look at some experimental results with tables. First kind is creeping flows, which are ones with really low Reynolds number, like less than 1 kind of low. In this situation, flow is very reversible and the shape doesn't have too much of an effect. So a sphere, hemisphere, circular disc normal to the flow or parallel to the flow end up with drag coefficients defined like this. So 24 over Reynolds number 22.2, 20.4, and 13.6 over the Reynolds number, with Reynolds number using the diameter shown here as its length factor. The velocity for Reynolds number would be the free stream velocity. Next, we're going to look at some 2D flow. This is for cylinders, so things coming out of the page that are long in that direction. We're going to take their length out of the page as b and assume that b is fairly long so that we can take this as two-dimensional flow. Then the D shown in the picture is the one to use for Reynolds number unless otherwise specified, so that the area is B, the distance out of the page, times D, because that would be the frontal area of all of these shapes when facing the flow. Drag force would then be the drag coefficient given in each of the pictures, multiplied by the area times rho v squared over 2. V being the free stream velocity. So we've got square rods, just rounding the corners changes the drag by almost a factor of 2. Then rectangular rods and rounded front edge rods. So if it's got sharp corners or rounded front edges, then we have some different kinds of drag coefficient. Just to check, the rectangular rod that's a square should be the one where L over D is equal to 1, and indeed we do get the same drag coefficient as we did in this case. Great. We have a circular rod and then an elliptical rod. As we increase L, that increases the streamlining, so an L over D of 8. Depending on whether the flow is laminar or turbulent, we have different drag coefficients. The drag coefficient, interestingly, for a circular rod versus a longer elliptical one, notice that the drag coefficient goes down, and since the drag force would be based on the frontal area, which is the same, just making the rod longer actually lowers the drag. This is because it causes a smoother transition, which means that less flow separation is able to happen, and we don't have as much of an effect from the difference in pressure in the wake region to the front. Looking at some other shapes, equilateral triangular rod, depending on if it's going into the flow or going against it like this, we have a different drag coefficient. And a semicircular shell, these ones are not hemispheres, they go out of the page like that. If it's hollow versus filled, you have differences in drag coefficient as shown. Following that is a similar table for three-dimensional shapes, which you can see by the cool lighting effects that the textbook has in these graphics. The parachute is one of the highest kinds of drag coefficient you can get for this sort of a shape where it's really scooping a lot of air, designed to have a lot of drag, so that makes sense. And these are all for turbulent flow. So based on a frontal area of CdA rho v squared over 2, where v is the upstream velocity, and are for, again, turbulence unless otherwise stated. So there's a few of these ones that also give you results for laminar flow, like the sphere. And even when it says laminar, it still isn't talking about Stokes flow. So those are the ones we had earlier for Reynolds numbers less than 1, creeping flow, Stokes flow. 15.5, parallel flow over flat plates. This is also the start of lecture number 11. So here what we're looking at is we've got some flat plate, which is along the bottom here, and we're looking at flow over it and what kind of drag is created. This is like a 2D extension of what was going on with the internal flow in the last chapter. So now, because there's no boundary layer from the top that comes in and collapses and causes the flow to become symmetric as you move, or not symmetric, but two-dimensional, or even one-dimensional, fully developed as you move along the inside of a pipe. Over a plate, in this sort of two-dimensional flow approximation here, the Reynolds number that matters uses the length of the top of the plate. So if the plate ends here, then you'd use this length as the Reynolds number, but if the plate keeps going, then the length increases, and you end up with the ability to get turbulence just from having a longer plate rather than a higher speed. So the laminar boundary layer occurs at the beginning, then you'll have a transition region if the plate keeps going, and eventually a turbulent boundary layer, which has increased amounts of drag due to the extra mixing from the free stream. Increased amount of drag for the thickness of the boundary layer compared to what you would get in laminar. All right, so looking at this, we've got a friction coefficient, which is like a drag coefficient, but only taking account of friction drag, skin friction drag, which, since we're talking about a thin plate, is the only kind of drag that we have. Boundary layer thickness corresponding to local friction coefficients are these delta, and or rather boundary layer thickness and the corresponding local friction coefficients are delta and CFX, but you don't care about CFX, the local one, because you really want to integrate and find out what the effective skin friction coefficient is over the entire length of the plate. And that's what is tabulated here. So if you have one where the Reynolds number using the entire length of the plate stays laminar, which for these plates turns out to be less than about 500,000, then the skin friction coefficient is like this. That's the one that you would use over the entire plate. So how do you use this? You take it and multiply it by half rho area of the plate, which would be the length, and then the times the amount out of the page that it goes. That's the area to use. And so that's the area. Half rho AV squared times this coefficient will give you the drag force along the plate, which is the thing you'd normally need to calculate. So for the turbulent one, we can ignore the laminar part. If the plate is long enough, we'll say, the laminar was a small part of the region anyway, most of it's turbulent, so let's just calculate the turbulent drag. If it's a smooth part, smooth surface, and you want to include the laminar part at the beginning, then you can have this correction factor subtracted from the previous one. This is typically small for large Reynolds numbers. And if it's a rough surface, then you should really be using this formula instead. So you can see that the effective skin friction coefficient is increasing a lot more with extra roughness, like we had for turbulence friction factors back in internal flow. 15.6, flow over cylinders and spheres. Now we're going to use the diameter as the characteristic length, which leads to a critical Reynolds number of about 200,000 for smooth surfaces. Laminar flow then happens at less than 200,000. Transition starts there, and we have turbulent flow above 2 million. Quite different numbers than we had for pipe flow. These three regions always exist, but the exact Reynolds number that they occur at differs for different types of flow. So in pipes, flat plates, cylinders, and spheres, and is strongly influenced by surface roughness. Surface roughness increases drag for streamlined bodies, but for smooth, bluff bodies like cylinders and spheres in high Reynolds number flow, most of the drag is pressure drag anyway from the difference in pressure from the front and the back in the wake region. So there's certain instances where extra friction can decrease the drag, check this out. If we increase the friction right here, then what we can do is cause turbulence, which has a lateral mixing effect and actually delays the boundary layer separation. This is the situation in this sort of a flow here. So here we've got something, we've put a little bit of a lip on this ball and flow to cause the thing to trip into turbulence sooner than it normally would. So here we have a smooth ball and it sees, okay, smooth flow, laminar flow the whole way along, have this big wake region with a lot of difference in pressure from the front and back. But here we trip it into turbulence, causing this lateral mixing that means actually a smaller wake region than we had here. So this has lower drag than this does, even though it's in turbulent flow. Yes, this friction drag is higher on this thing, but friction is so much smaller of a fraction of the drag at these Reynolds numbers for this kind of a body, like not a flat plate like we had in the last section, that even though the friction drag is higher, because the form drag is lower because of the smaller wake region, it actually can make a difference. Now, this is only in a certain region, which happens to be exactly around where the golf ball is. So for the size of a golf ball, if it wasn't dimpled to kick it into turbulence earlier, then you would have a higher drag coefficient. You would have higher amounts of drag because the flow stays laminar. As you increase the Reynolds number around this area, then even for a smooth surface, like this solid green line here, the drag will eventually be associated with turbulent flow above what we were saying up here is transition happening at 200,000 and then turbulent flow above 2 million. So once that's happened, then the drag kicks down and reduces as you go into turbulent flow. So why is the drag lower in turbulent flow? Again, because turbulent causes a smaller wake region and most of the drag is due to this form drag anyway. This is, again, just the drag coefficient, not the actual drag force, which is proportional to velocity squared. So even though the drag coefficient is lower here than it is here, because the velocity is changing by orders of magnitude, the drag force is a lot higher over here than it is over in this area. For anything in this region up here, you could get lower drag by roughening the surface and causing it to trip into turbulence sooner than it normally would. But once it actually is going to be in turbulence anyway, the extra roughness doesn't help. It just would cause increased drag on the surface. 15.7, lift. Lift coefficient as drag coefficient gets multiplied by half rho v squared times a, except the a for the airfoils that we're going to deal with is not the frontal area, but the planeform area. This is the chord length, the distance from the front to the back of a wing, multiplied by the span. That's the planeform area of the top of the thing. And the lift that you would get for a symmetric airfoil is 0, stagnation point to the front and back. If you were to assume that the flow is irrotational, then it turns out an asymmetric airfoil should give you no lift either, but the flow actually has some rotation to it. So some rotation at the front and then rotation going the other way at the back is responsible for the stagnation points being able to be where they actually are around an airfoil. And this gives you a lift force. So it's easy to look at this and say, it's simple because it forces air to go faster around the top, and that means it increases speed and reduces the pressure, and that doesn't happen at the bottom, so you have higher pressure on the bottom and lower pressure on the top, and that's true up to a point, but there's also complicated effects from vortices that show up near trailing edges and then on wing tips. So if you want to get a true answer, then you really have to do some experiments or some pretty complicated CFD. Anyway, looking at the sort of plots that we have of lift coefficient relative to drag coefficient and then lift coefficient on their own for various types of airfoils, we can still do some calculations with this and make some generalizations to help our understanding. So if you have slots in the thing or a higher angle of attack, then generally this increases both the lift coefficient and the drag coefficient. This is not so bad of a thing to do when you need maximum lift and don't care about so much of the drag force. And that's the case during takeoff of a plane. So while you're taking off, these modern aircraft will often have flaps that will extend out in order to increase the lift coefficient at the expense of increasing the drag coefficient. And that means that you can get a maximum lift coefficient and take off in less runway distance. Yes, it uses up more fuel because you have a higher drag coefficient at the same time, but that's not so much of a problem. On the other hand, when you're cruising at your altitude up in the sky and you're just maintaining speed there, then you want to minimize the drag, so the flaps will often close so that you get less lift, but you also reduce the drag by a fair bit. So you care about having maximum lift, not caring about how much drag you have when you're trying to take off, and then you want the highest lift to drag ratio when you're just cruising along.